Hey, good afternoon. Today's going to be our last lecture on binary relations. It's lecture 18. So we're going to do some review from the last couple of classes, and then we're going to talk about some of the things you'll need for your homework. So again, what is a binary relation? It's a subset of a cross product. So if you get out of this class, at least you'll know that. And what are they good for?
Airline tickets.
They're good for airline tickets, but they're good for representing any time you have a relationship between two things. So, like if I wanted to list like all the people who are related to each other at NC State, you know, by family, I could make such a list, and I could use that to figure out whether, you know, if someone's writing a recommendation letter for somebody, if it's actually their cousin or something. Okay, so there are lots of uses for binary relations. Anytime we want to know about relationships, it's a way to quantify those relationships and put them down in a set for us. Okay, and we've been talking about special relations, which are relations just on one set, so something like S cross S. So all the properties we've been talking about are for relations just on a single set. So things like reflexive, irreflexive, symmetric, anti-symmetric, and transitive. You already have all of these. I just want to remind you what they are. You have them in your notes. And we have one more, right? Yeah. Asymmetric.
Asymmetric.
I never write them all out. Just write it so you know which one is which. So I think that the two hardest, what are the two hardest out of this list? Anti-symmetric and transitive, right? Yeah. But there's actually some tricky ones too, though. Reflexive is easy. Irreflexive, though, is not just the opposite of reflexive. Don't forget that. Okay, so if you think about the matrices, reflexive has all ones on the diagonal, right? Irreflexive has all zeros. So there's lots of diagonals that aren't either all ones or all zeros, right? I could have 0, 1, 0, 1 all the way down the middle, and that would be a valid relation, but it's not reflexive or irreflexive. So there's tons more that aren't either one than there are reflexive or irreflexive. So they're not opposites of each other. And symmetric and anti-symmetric are not opposites either. Okay, so just because you have one doesn't mean you don't have the other, although it means you probably don't. So, but you still have to check. Okay, so anti-symmetric is the hardest because it has a complicated definition. It's not hard because the concept is not hard. Okay, asymmetric, so we understand symmetric really well. If we have x relates to y, this is another way to write x, y as in R. That's just another way to write it. X relates to y. That implies that y relates to x, right? Yep. Well, asymmetric just says if x relates to y, that means that y does not relate to x. And that's easy to see. So if I look at a set, I can just tell immediately if there's anything and its reverse, it's not asymmetric. So I can have 3, 1, but I can't have 1, 3. But asymmetric, the special thing here is that x relates to x is never true. So x can't relate to x, because if you look at this implication, it has to work for all x and y. If I put x relates to x in there, then that implies that x does not relate to x, which is false. Right? So I can't put XX in there, which is the only difference between asymmetric and anti-symmetric. It's just that in order to write that difference down, it makes this definition look a lot more complicated. But it's not. Yes?
Can I write y not relates to x as not y relates to x?
Yes. That's equivalent. So y does not relate to x can be written as a not outside of y relates to x. Those are equivalent ways to write that. And this one is less ambiguous because sometimes you might not see the slash through the R. Okay, so antisymmetric is just like asymmetric, except what?
X is not equal to Y.
X relate to X is allowed.
Zoom out.
That's the only difference between those two. So let me make that actually bigger. Antisymmetric is just like asymmetric, except X is allowed to relate to X. That's the only difference between the definitions, because asymmetric is what? Antisymmetric and irreflexive, right? Yes. Question?
Is it possible for a relation to be neither symmetric, antisymmetric, or asymmetric if it has a
That's
special
right. It
definition?
is possible to be not symmetric, not antisymmetric, and not asymmetric. So what would a relation look like if it was that? We can look at a matrix and tell. So
0, 1, 0, 1.
So if I don't want something to be asymmetric, all I have to do is mess with the diagonal, right? I can just put, let's just say I have 1, 2, 3, 1, 2, 3 here. So let's make that bigger. Okay, if I want to make this not symmetric, I just have to put a 1 and a 0 across from each other. If I want to make it not antisymmetric, I just have to put a 1 and a 1 across from each other. And that's it. I can fill the rest with zeros. So this is not symmetric because of these two, right? It's not antisymmetric because of these two with little stars next to them. Okay? And it can't be asymmetric if it's not antisymmetric. Does that answer your question? Okay, so we don't have to have any one of them. We can have none of the properties, and we can actually have all of them. If your matrix has all zeros, you can have all the properties, except for reflexive.
Once again, the ones at the diagonals means not asymmetric.
If there's a 1 on the diagonal, that keeps it from being asymmetric. No matter, even if it was antisymmetric, it wouldn't be asymmetric if there's any 1s on the diagonal. Right? Because asymmetric means it's irreflexive. You have to remember the definitions. So that's all that we're going back to on these properties, because that's all they are, definitions. And we just check the definitions, and if they're true, then we have the property, and if they're false, we don't. So again, we're going back to our true-false things like we've been doing since the beginning of the semester. Okay, so we remember that reflexive has what in the matrix?
One.
One's on the diagonal.
So it has all 1s on the diagonal. Irreflexive has what?
Zeros.
Is all zeros on the diagonal. That doesn't mean that you get to forget the predicate calculus definitions of these things. You have to know them, and you have to be able to use them. But this is if you have a matrix, you can check it faster by knowing these. So symmetric means what? That means that the elements across the diagonal match each other. So if I have a 0 on one side, like at 3, 2, then at 2, 3, I have to have a 0 for that. So this is, it's sort of the mirror about the diagonal. So if I fold over my matrix at the diagonal, if I fold it over, then it's the same above and below the diagonal. Those triangles are the same if I fold it over. Antisymmetric just means if you fold it over, then I can't have 1s on top of each other. So if I draw my matrix, let's make this bigger. Remember I drew 3 sections last time? If I fold it over, I'm allowed to have, so if I fold these and match them up, so I'm allowed to have 0, 0 if I fold them over. I'm allowed to have 1, 0, and 0, 1, but I'm not allowed to have 1, 1. So that's for anti-symmetric. So if I look at that triangle when I fold it over, so like if I root the number from the top and then the number from the bottom, I can have 0, 0, I can have 1, 0, I can have 0, 1, but I can't have 1, 1 if I fold them over. Are there questions about that?
But you can't have 0, 0?
I can have 0, 0 because it's an implication, right?
Okay.
It says if x is not equal to y and x relates to y, then y can't relate to x. But if the hypothesis is false, then the entire implication is true. So I'm allowed to have 0, 0. So a matrix with all zeros is anti-symmetric. So just because I have a 0 doesn't mean I have to have a 1 across from it. That's why that makes this definition confusing. Because I'm allowed to have 0, 0. Like asymmetric has to have, asymmetric also allows this. Right? But it doesn't allow it on the diagonal. So no 1s are allowed on the diagonal for asymmetric.
Gotcha.
So in transitive, we can't just look at the matrix, right? We have to do the matrix composition with itself and check to see if the composed matrix R squared is a subset of R. Does everybody remember that? Blank stares. Okay, so we cannot check a matrix just by looking at it for transitive. I keep pressing the wrong button. So this is one definition of transitive. R squared is a subset of R. Because R squared was, if I take a matrix and compose it with another, if I take a relation and compose it with another relation, then if AB is in the first one, and remember we have to go from right to left for these. If AB is in there and BC is in there, then when I compose, that means that AC is in the composition, right? So if this is in R and this is in R, then this is in R composed with R. So that looks just like the definition of transitive, and that's why R squared is a subset of R is the same as saying that R is transitive. Because this is R squared. But transitive says if I have AB in R and I have BC in R, that means that AC is in R. So if everything that was in R squared is also in R, then that means my relation is transitive. So this is the definition of transitive, and this is from composition. So they're almost exactly the same, and that's why R squared is a subset of R, tells us whether we have a transitive relationship or not. So you can't just look at a matrix, you actually have to multiply it by itself and then see if all the new points in there were in the original relation. So let's do a matrix and see if it's transitive. So we just looked at a matrix. We had 0, 0, 1, 1, 1, 0, and 1, 0, 0. This one wasn't symmetric, it wasn't asymmetric, it wasn't antisymmetric. So now we're going to see if it's transitive. So we have to do matrix composition, so that means we have to multiply it by itself. And it's row by column. So when I turn this row down this way, I get 0, 0, 1 in a column. So that's row 1. So when I compose those, this one picks up which row out of here? 1, 2, or 3? 3. It picks up the third one, because remember our magic wand method? The 1, we turn it sideways, and the 1 sweeps across and picks up the row. So that 1 picks up 1, 0, 0 from the bottom. In the second row, I have 1s in the top 2, so I'm going to pick up actually the top 2 rows and OR them together for my matrix composition. So I'll pick up 0, 0, 1 and OR it with 1, 1, 0 to get 1, 1, 1. And in the third case, this one's going to turn sideways and just pick up the top row. So that's going to give me 0, 0, 1. So now this is R squared. If this was the matrix for R, This is now r squared. Now I have to check to see, is r squared a subset of r? So what does that mean in terms of these matrices?
Well, the first one would represent 1, 1, which is not in R.
Right, so I have to actually check. Every single one in here has to be a 1 in R. That's what I have to check for subset. So here I have a 1 at 1, 1, which is what your name is?
Jeff.
Jeff. So Jeff was saying that we have 1, 1 here, but we don't have it in R. This is R also, and so is this one. So these top two ones are R. I don't have 1, 1 in there, so R squared can't be a subset of R. So it's false. So R is not transitive. So just to double check that, let's draw a picture of this relation. So we have 1, 2, and 3 all relating. So in our relationship, we had an arrow from 1 to 3. We have 1 from 2 to 1, and 1 from 2 to 2. And we have 1 from 3 to 1. Okay, so in our composition, we got 1, 1, and that was the result of taking a path of length 2 in our graph from 1 to 3 and 3 to 1. If this were transitive, then I could go on a path of length 1 from 1 to 1. That's what transitive does. So if I had 1 to 3 and 3 to 1, I'd be able to go 1 to 1, which I can't. Yes?
So that's one of my questions. If you have a case like that, like 1 goes to 2 and 2 goes to 1, for it to be transitive, you have to have 1 to 1.
I absolutely do. Right, so this point here, 1, 1 is here because I went from 1 to 3 and 3 to 1. That's where it came from, because this says 1 to 3, and then 3 went to 1. That's where that 1 came from. So that was this edge here and that edge there, making a path of length 2, and that means I should have had a path of length 1 from 1 to 1. So this relation r squared is not a subset of R, so it's not transitive. What's your question?
Need 3 to 3.
I would also need 3 to 3 because I can go 3 to 1 and 1 to 3. So all the ones here that are missing, those are missing, and this one is missing from R also. So this one says that we should have 2 to 3, right? Because that's 2 and that's 3. So I should have 2 to 3, and why is that? Because I can go from 2 to 1 and 1 to 3. So I should have had 2 to 3 in this also for it to be transitive. Now if I wanted to do the transitive closure, I'd have to add these, right? But then I'd also have to check after I add those and make sure it's transitive. So let's do that, actually. If we add those, then we add 1, 1, and 3, 3, and 2, 3. Then that might make it transitive, but I have to check. So this is our new relation, actually. Because if I take, actually I have to put this one in here too. So this one. So R union with R squared is what I'm going to try to see if it's transitive or not. I'm trying to make the transitive closure now. So that's going to be 1, 0, 0, 1, 1, 1, 1, 0, 1. Then we'll have to square that to see if it's transitive. Right? Because I don't know if it's transitive yet.
Are you sure about the 2, 3?
2 goes to 3? Yeah, because it's in R squared.
Okay. All right.
Because I had 2 goes to 1 and 1 goes to 3, so I really have to have 2 goes to 3 to make it transitive. So you can always check the edges that you add and make sure that you should have them.
All right. Well, was 3 goes to 1, since it was in the original, shouldn't it be in the...
It is.
transitive
This is
closure?
in the union right here. This is what we're going to test now. We took the union of R and R
The
squared.
top right corner.
1 goes to 3.
1 goes to 3.
1 goes to 3?
Yeah.
Oh, sorry. That was a mistake.
Yeah.
Sorry about that. That should be a 1 there.
Yeah, it should be 1.
So we're going to test 1, 0, 1, 1, 1, 1, 1, 0, 1, and see if it's transitive. So this is R union R squared, but we have to square it to see if it's transitive. So we wanted our final result to be transitive. So if we compose it with itself, if I turn this sideways, that picks up the top row and the bottom row, right? And ORs them together. Top row and the bottom row gives me 1, 0, 1 because they're the same. This one picks up all three and ORs them together because it's 1, 1, 1. If I sweep it across, it picks up all three rows, meaning it picks up the middle, which is 1, 1, 1. And the last one picks up the same as the first one, so I get 1, 0, 1. This is the same matrix back, so it has to be transitive. So all we had to do was one union, so R union R squared is equal to the transitive closure for R in this case. So you're not usually, like if you have a 3 by 3 matrix, you probably won't have to compute anything more than R cubed. So remember that the transitive closure, what was the transitive closure? We had a general definition for a matrix R, for relation R. The transitive closure was the union k equals 1 to infinity of R to the k. Right, and we started that process. We unioned R squared with R. And then if that didn't work, I would have had to union R cubed. But that was already transitive, so I could stop. So normally, you won't have to go any more than the size of the matrix. So if it's 3 by 3, you won't have to do more than R cubed. So it really doesn't go up to infinity. But if you want a general definition, it has to. Right? If it has to work for everything, it has to go up to infinity. But it ends up, you start getting the same thing over and over again, because if I take the union of this with this, I get back the same thing. So I don't have to compute anymore.
Which we just did.
Right. It's good to know when you can stop, right? You don't want infinite loops, ever. So we have one here, but you get to stop early. Are there questions about this? So now we know we can't just look at a matrix and tell if it's transitive. There's no way you can look at it and tell. You have to square it, or you have to check every pair of edges and make sure that you have the transitive edge. Questions about that? Yes.
It kind of looks like the output from when we were doing the circuits. So are we going to use this and kind of use it to get big O again, or is this something totally different? Because then if you can go up to R cubed, then would that make it that whatever function would output that would be in R cubed, or is this something different?
Matrix composition isn't quite the same as cubing functions.
Okay.
So it looks similar. It might look a little similar to the big O stuff. And I'll think about that. And next time I'll tell you if there's a relationship. But in general, I don't think about big O and this in the same sort of sections.
So R cubed is basically just another name for R for 3x3 size.
R cubed is the same as R composed with R composed with R.
Okay.
So all that means is that there's 3 of them composed together. Do matrix composition 3 times.
Okay.
Which ends up being a matrix multiply, but that's different than a regular multiply.
Right.
It's actually like a set of equations. And doing the matrix multiplication is a lot easier than writing all the equations. Right? Because we would have had 9 equations here. And that's why matrices are very cool, and that's why it's really good for computer scientists to be good with matrices, because you're going to end up using them to represent things a lot. So everybody knows that this would be represented. Well, how would you represent this in a computer? A matrix.
Array?
In an array, right? So I could use a 9 by 9 array, sorry, a 3 by 3 array for this, right? It will have 9 elements. And in memory, how is it actually stored?
Bunches of addresses.
Sequentially.
It's usually stored as a linear array, just a 1 by 9, right? So actually, if you had to do your own memory management, you'd actually have to write an equation for making this a 2 by 2 array. And I have to do that in the program that I'm doing for your tutorials. I actually have to make my own memory, so it's really good practice for me. But so these matrices are usually stored linearly. I just wanted to point that out so everybody would know. So if I wanted to write an equation to address one of these, and suppose I put one row after another, so I would have had to put this row, so 101, 111, 101. I could write an equation to access those, right? So I would have a little function matrix AB. And then what do you think it would be?
A times 3 plus B.
It's probably, assuming that I want to start at 1, maybe. Okay, it makes a difference if you start at 0 or 1, right?
Yes.
So I want it to be 3 times A minus 1 plus B. I've just been doing this so much now, I don't even have to think about it. So if A is 1, if it's the first row, it will be in the first 3, right? So I want it to be 3 times 0 plus whatever B is. If it's in the second one, I want it to be 3 times 1 plus whatever B is. It's going to be 1, 2, or 3. If it's in the third one, I want it to be 6 plus whatever, whichever one it is. So it's good to get used to doing these kind of calculations and stuff. Okay, let's move on. Let me check through the packet and make sure I've talked about everything. So let's all go to page 5 in your packet. So in the packet, we have a page that has a diagram of some examples, and it tells you some of the properties of them. So we've done is a factor of, we've done it in class, right? And is a factor of, what kind of relation was that? It was partially ordered set, right? It's a partially ordered set. So that means it's what? Reflexive, antisymmetric, and transitive, because partially ordered sets are like less than or equal to. So, and less than or equal to is reflexive, antisymmetric, and transitive. So when you're trying to remember antisymmetric, remember less than or equal to. That's how it works, the same way as less than or equal to. So this one's reflexive because x is a factor of x, right? It's not symmetric, and here it has an example. Let me see if I can zoom in a little. 2 relates to 4 because 2 is a factor of 4, but 4 does not relate to 2. So it's not symmetric. It is antisymmetric because I can't have 2 relates to 4 and 4 relates to 2. I can't have anything like that. If x is a factor of y, then y can't be a factor of x unless x and y are the same. That's really fundamentally how antisymmetric works. I can't reverse the order of an ordered pair unless it's actually the same number. Okay, and it's transitive because if I have x is a factor of y and y is a factor of z, then x is a factor of z. So a lot of, like if I give you a test, I'm going to give you relations like this where I'm going to be able to tell without like checking every single pair of points what the properties are. So less than is also like a partially ordered set because it's like less than or equal to, but it's not reflexive, right? So it should have antisymmetric and transitive. Right? And the star is here because it's also asymmetric because this is irreflexive, right? Y is less than irreflexive.
Because you can't have one being less than 1.
Because I can never have x less than x. That's always false no matter what x is. Okay, so what does congruence mod 5 mean?
If you divide both
X
numbers
minus
by
5 is reducible by 5. Minus.
Congruence mod 5 is that funny thing I wrote before. So we draw those triple lines. So that's what congruence is. I just wanted to go over this to make sure you know what everything means. Congruence mod 5 is that equivalence sign. That's what those 3 lines mean. It means equivalent mod 5. So if I divide both of them by 5, I have the same remainder. That's what that means. And this is an equivalence relation. So anytime you see the same or equivalent to in your definition, you know it's going to be an equivalence relation. You know it's going to be reflexive, symmetric, and transitive. Then the last one we have on the sheet is subset. So this is, we drew that diagram last time that ended up looking like a cube. We had the power set of the set 1, 2, 3. And down at the bottom it had the empty set, and up at the top it had 1, 2, 3. And in between it had all the subsets. So this was reflexive because any set is a subset of itself. It's not symmetric because I can have the empty set is a member of 1, but 1 can't be a member of the empty set, the set containing 1. It's antisymmetric because this can never happen. or I mean, because that's always true, and it's transitive also, because if A is a subset of B and B is a subset of C, then A is a subset of C. It's just because of the way sets work. And any questions about those? So these are some examples of like categories of relations. Okay. If you have any other kinds of questions, you should ask. Let's see. We've talked about the digraphs, so I'm just looking at the notes, making sure we've gone over everything. You should be able to review these on your own. It's got some help on using the matrix on page 7, using the matrix to check for properties. We were just talking about that. Has a little bit about composition on page 8 and 9, and equivalence relations, partially ordered sets. And page 10, I wanted to go over this class lemma. Okay, the class lemma is, and we're going to use this on our homework, so the class lemma says, if A is a subset of B and C is a subset of D, then what do you think is true? And I want you to think about constructive dilemma.
A or C
is a subset of D or D.
Except these are sets, so I'd have to use union and stuff like that, right? So there's several things that are true. A union B is a subset of B union D. A intersects C. Sorry, that should have been C there.
Yeah.
So I have to combine the left-hand sides and the right-hand sides. B intersect D. But also, one other thing is that A composed with C is a subset of B composed with D. And likewise, C composed with A is a subset of D composed with B. And that's because composition is a combination of unions and intersections. And it works exactly like constructive dilemma does. So as long as you do everything in the same order, so notice that I had to put A composed with C and B composed with D. It really mattered which one came first. Because compositions in other directions are, if I multiply two matrices, it really matters which one comes first, what the product's going to be. And then C composed with A had to be a subset of D composed with B. You're going to use that in your homework. So let's do a little proof of this, why this works. So this is in your notes, so you can go over it with me in your notes. But I'm not going to use R1 and R2 because A and B are easier to see. So if I have A as a subset of B and C as a subset of D, I'm going to prove that A composed with C is a subset of B composed with D. So let's just suppose that I have a point, x, y, in A composed with C. So what does that mean? Whenever you do a proof, you have to know what everything in it means, because that's probably going to get you your next step. So what does it mean that x, y is in A composed with C?
A composed with C is not the empty set?
It means that. But how could I have gotten x, y in there in the first place? From A and C. So the idea is I have to get back to my given. So I have to figure out something about A and something about C. If xy is in A composed with C, then C had to have xz, maybe, right? So I have to have an xz in C and zy is in A, right? Because otherwise I couldn't have gotten xy in there. I don't know what z is, but there is some z. There exists a z. So that implies, because of the definition of composition, that I have to have those 2 points. Okay, but if I know xz is in C, then where else is it also?
Also in D.
So using our givens, if xz is in C and C is a subset of D, then what?
Yes,
X is in D.
XE is also in D. So this is definition of subset. And likewise, I can do the same thing with ZY. That's in A, but I know A is a subset of B, so ZY has to be in B, right? So if I have X, Z, and D, and I have ZY and B, then what? If I do D first and then B second, then XY has to be in D composed with B. Right? So if I have both of these, then that means that XY is a member of doing D first and then composing that with B. So let me put some line numbers on here. So this one came from 5 and 7 in definition of composition. And I have to sort of go the other way, too. So now I've proved that if XY is in A composed with C, it has to be in B composed with D. I actually don't have to go the other way because all of these are now in there. Anytime I'm in A composed with C, then I'm also in, XY is also in B composed with D, which definitely means that's a subset, right? That's how I prove a subset. If there's a point in here, it has to be also in there. So I'm done with the proof. So therefore, so the last line would say, so it wasn't a hard thing to prove. I just had to use the definition of composition. And I know that it takes a while to get used to. And that you're thinking, oh, Tiffany's been doing it forever. It's really easy for her. But the more you do, the more you'll understand what composition means. And that's why I do these examples and exercises for you to show if you keep using the definition, you'll start to see stuff. I don't expect you to be wizards at anything at first. Just after you do all your homework, you will be. So, and there was a typo in your homework. I'll go fix it. But for those of you who've already printed out the homework, it says problem 10, and then it refers to some problems 12 and 13 on there. So let me just mention the correction on that. You have two problems. Remember last time I told you you were going to have to prove some closures? That's what 8 and 9 are on your homework. So problem 8 and 9, the first one I think is the symmetric closure, and the other one is, no, the first one's reflexive closure. It gives you the matrix for reflexive closure. The next one is you have to prove symmetric closure. And then 10, it says prove from 12 and 13 some stuff. You know, it says you have to prove that R is a subset of RC, and B, RC has a property. Okay, this is just reminding you what you have to do to prove these closures. So this is not another problem. So this is not another problem. I'm going to fix it, but in case you've already printed it out. It's just instructions for 8 and 9. And so 12 and 13 should read 8 and 9.
But A should be RC is a subset of R. They are not the same thing, right? RC is a subset of R.
No, R is a subset of RC if RC is the closure that you're trying.
Another typo there. We have to see the picture of that.
Let me see. Homework paper. Yeah, that is a typo. I didn't read over Andy's, so I apologize. I will go fix all the typos. This is what it should read. R is a subset of RC. You already have that in your notes, right? So also on page 10, it has a definition of closure. The closure has to contain R, has to have the property that you want, and has to be minimal. So that was the third thing. You have to show that it's minimal. And we did that by contradiction. You have a question?
The first word in problem 8 says show that the relation R on the finite set A is represented by matrix MR. But problem 9 says suppose that the relation R on the finite set A is represented by MR.
I'll go over it and fix the word. You need to prove that the matrix written there represents the closure for R.
Okay.
That's it. So whatever it says, it should say, if it's a reflexive closure, should say the matrix for R ORed with I sub n, where I sub n is the identity matrix, represents the reflexive closure. So this is the matrix for the reflexive closure. And we did the whole problem for the set, right? So the equivalent set for that was E, right? So that was E, was the set we talked about, where E had the points x, x, where x is in our original set. That was the elementary matrix, the relation. Does everybody remember what I'm talking about? Mm-hmm. Okay, good. Because I did this last time. I did the whole proof last time. So you actually are proving for the sets, but these are the matrix representations for the sets. So you just have to say, here's the proof. You can do it for the sets and say, these are the matrices that represent the sets. And OR is the same as union, right? So that gives you a formula. So whenever you want to do the reflexive closure for something and you have it in matrix form, you can just OR the identity matrix in and you have the reflexive closure. Right? So problem 8 is actually giving you a way to get the reflexive closure quickly. Is to OR the identity matrix with your original matrix, and then you have the reflexive closure. So problem 9 says that you do what? You OR the matrix with its transpose. So problem 9 says, so for the symmetric closure, it's the matrix for R ORed with the transpose of the matrix for R. What is transpose? You have to reverse the rows and columns. That's what transpose is. So I will go over and check that and make sure everything's typed out. It ought to be.
Is there an example of transpose? Exactly how you reverse the rows and columns?
We'll do one right now. And I'll do it in general, just so you can see, because if I put ones and zeros, you might look at it and some of the rows and columns might be the same. If I want to do the transpose of this, that's equal to taking this row, turning it sideways the same way I did like a magic wand. I turn it sideways like this. So AB now becomes a vertical vector, and CD now becomes vertical. So that's the transpose, where I take the first row and make it into the first column, second row make it into the second column, and so on.
So it's kind of like flipping it diagonally along.
I wouldn't think of it as flipping diagonally. I always do row by column. Take a row, make it vertical. But you don't flip it this way. That's the thing, is that you don't put the B on top. The A has to go on top, because you read it like this. The 1, 1 element has to go to 1, 1. The 1, 2 element has to go to 2, 1. The 2, 1 element has to go to 1, 2. And the 2, 2 element goes to 2, 2. So if it's a bigger matrix, it might not work the same way as you're thinking.
Well, it should flip along the diagonal.
Okay. Yeah, it does. You're reversing the top and the bottom triangles. Okay, so the last problem on your homework says to prove that R to the N is transitive. That's what the last problem says. And you have to use two things. You have to use that r squared is a subset of r is logically equivalent to saying that r is transitive. And you have to use the class lemma we just talked about. If A is a subset of B and C is a subset of D, then that logically implies that A composed with C is a subset of B composed with D. You have to prove this by induction. R to the n is transitive, so it's induction on n. So no matter how many times I compose a transitive relation with itself, it's still going to be transitive. And all of that should be written on your homework paper. Even though everybody's writing it again.
Just to drive you nuts.
Yes, I know. That's your job, to drive me nuts, and my job is to drive you nuts. I think we both are doing a great job. Okay, so if I have to prove this by induction, what's the first step?
Basis.
So this is a problem just like the Fibonacci problem on the test. It is not a hard problem. It's just that when you look at it, you go, oh my goodness, I can't do that. But you know how to do induction. Whether or not you know what the heck you're doing induction on, you can do it. So my basis is n equals 1. This is if what? If r is transitive, r to the n is transitive.
Yeah.
So I actually need that, if r is transitive. So for n equals 1, I have to prove that r to the 1 is transitive. But this is given, right? So that's already true. That had to be given, otherwise it won't work. R to the n just can't be transitive just any old time it wants to be. So I assume for n that r to the n is transitive. So using this number 1 up here, this alternate definition of transitive, what does r to the n is transitive mean?
That whatever n is, that r to
Composed with itself n times.
If you keep composing it with itself, it's still going to be transitive.
Okay, I want to rewrite r to the n is transitive using the definition given in 1. How do I write it? So you're telling me a lot of stuff, but that's not telling me how to write it.
R to the n is a subset of r to the n minus 1.
Nope. That was a good guess. R to the n is a subset of r to the n minus 1, but that's not what it is. If I want to prove that r is transitive, I have to say r squared is a subset of r. So if I want to prove r to the n is transitive, then r to the n quantity squared is a subset of r to the n. So this is the same as writing r to the n quantity squared is a subset of r to the n. But if I have something raised to a power and I square that, I just multiply the powers, right? So that's r to the 2n. So now I have my assume step. Now I need my prove step. So I have to prove r to the n plus 1 is transitive, and then I will be done if I actually get to prove that, right? So using this definition like we just did, how do I write that r to the n plus 1 is transitive?
R to the n plus 1 quantity squared.
R to the n plus 1 quantity squared is a subset of r to the n plus 1. Good job, Journey. So then I multiply the powers, right? So this is r to the 2n plus 2 is a subset of r to the n plus 1. So this is another case of having to be able to do your algebra, right? I'm going to have to use my exponents to now get this in terms of my assume statement. So I have r to the 2n as a subset of r to the n. And from my given, I actually know that r squared is a subset. R squared is a subset of r. That's a little squared up there. So how do I write? What I do is I start with the left-hand side of what I'm trying to prove, right? So r to the 2n plus 2 is equal to r to the 2n times what?
Times r squared.
Times r squared. And I needed that because I have r to the 2n in the given. That's why I'm bothering. So this is from the given. So from the given, I know that r to the 2n is a subset of r to the n. And our lemma said that if I had two subsets, I can do a composition, right? So I also know that r squared, see I have an r squared there, I needed a subset of something else. What is it a subset of?
R.
It's a subset of r because r was transitive, right?
Mm-hmm.
So that's a subset of r. So now this composition, because that's a little composition there, r to the 2n is times r squared, composed with r squared, is now a subset of these two composed, right? R to the n composed with r. And I will leave the final step to you. So anytime, by the way, anytime I work a homework problem for you in class, that doesn't mean you should just write it in and turn it in. You know, write it down, just what I did, and turn it in. Because sometimes I leave stuff out, for one thing. And I talk through it. And the other thing is you need to be able to do it yourself. So I do it for you sometimes because I know that something has a lot of symbolism in it. So you might not be able to do it just because you might get bogged down in symbols. But you need to be able to do it by yourself again. So the best thing to do is, sure, go ahead and write this down for your homework, but go ahead and sit down and try to do it again by yourself without looking at anything I wrote. So I had a guy come to the office the other day to take the test, and he was like, I could do all this stuff yesterday, but I can't do it today. And the reason is that he always had another problem in front of him, and he was copying how to do the problem. So if you want to study for the test and you want to do a good job on the test, you know all of our tests are closed book, right? So you can't have another problem in front of you when you work these. You can do it the first few times, but you need to be able to do it without another problem in front of you. That means you have to understand really what we're doing. What does induction really mean? I have to have a basis. I have to start with a starting value. I have to plug the things in. You know, I have to write the statement over for n, and I have to write it for n plus 1, and then what do I do after that? And you can't be looking at something else all the time. The first 20 times you do it, you can, but the next 20, you need to take the stuff out of the way and try to do it without it. Okay, so are there questions about this one? This ends up proving what we wanted to because there's only one more step left. So on page 11 of your notes, we're not going to go over this, but on page 11 it has the proof that the transitive closure is the infinite union of all the r to the k's, the thing I just gave you, has a proof on there. So take a look at it. Has some interesting stuff with equivalence relations in here. And on the next page has a little bit about partially ordered sets and Hasse diagrams. This homework, by the way, does not have Hasse diagram problems on it. Your graph theory homework, the last homework, is going to have Hasse diagrams. So don't forget this. Don't lose this packet before homework 10 rolls around in 2 weeks because you'll need it. Okay, so the Hasse diagram stuff is not on this homework, but it is going to be tested. And it's going to be on your homework and it'll be on the test, on a test. Okay. So we started with that early because Hasse diagrams are a little confusing. That's why I started with those really early. So you'll get a look at them a few times. So on page 15, if you don't have your notes with you, I'll put it up here, is that same diagram I drew last time for the power set. We had a partially ordered set that was defined by the relationship was on the power set and our relation was subset. So this is our Hasse diagram. So remember that a Hasse diagram is just a graph, but we drew it so all the arrows actually go up, right? And we didn't draw the reflexive points, which are little loops on every single one of these points, because all of these are a subset of themselves, right? And the last thing is we didn't draw transitive edges. So I didn't draw an edge from the empty set to all these other points except for on the first level. Because then that simplifies the diagram a lot, and then I can read it better. That's the whole point of doing that. So if you want to take a relation and make a Hasse diagram for it, like say you're given a picture of a relation. It says make a Hasse diagram. You just have to rearrange it so that it does this. So let's make a general one. Thank you. Let's see, I have to Okay, I hope that's a partially ordered set. We'll find out. Okay, so on the bottom level, I have to put stuff that doesn't have arrows going into it. So what goes on the bottom? 1 and 3 go on the bottom because they don't have any arrows going into them. Now, 2 can't go on the next level because 4 actually goes to it, right? So 4 can go on the next level, though. So 1 goes to 4 for sure, and 3 also goes to 4. And 2 has to go on the next level because 4 goes to 2. And we already have that 1 goes to 2 because 1 goes to 4 and 4 goes to 2. And 3 goes to 4 and 4 goes to 2, so I don't draw a 3, 2 line. So this is the Hasse diagram, only I actually shouldn't have drawn those little arrows. Okay, so remember that we talked about minimal and maximal elements for Hasse diagrams last time? So minimal ones are just stuff that you can't go down any further, right? So what's minimal in this diagram? So let's draw boxes around those. These are minimal. And what are maximal elements here? 2 is maximal, and there's no others. So is there a maximum in this Hasse diagram?
Yes.
Yes, 2 is a maximum because there's only one maximal. Are there any minimum elements? No, because there's not just one minimal element. So there's no minimum. So no minimum in this Hasse diagram, just a maximum.
Is there a special name for 4?
Is there a special name for 4? No. There's nothing fancy about 4. It's just in the middle. Okay, so anytime you're given a relation, whether you're given a list of points or a matrix or another picture, you should be able to make a Hasse diagram. Okay, so let's talk about one other thing with Hasse diagrams. And that is upper bounds and lower bounds. So someone wanted to be related back to big O. This kind of relates back, but not quite. It's a similar thing, though. We want upper bounds for things, but that's using the Hasse diagram. So if I want an upper bound, all the upper bounds for 1. So that's everything I can get to by staying at 1 or going up from 1. It's an upper bound for staying at 1 because actually 1 really does have a little loop going to itself, right? So upper bounds is all the stuff I can get to from 1 by going up. But since 1 relates to 1, it's actually, you're going on an edge and getting back to 1 because it's really reflexive. So what are the upper bounds for 1?
1, 4, and 2.
So that's 1, 4, and 2. So all the upper bounds are 1, 4, and 2. What did you write? UB is upper bounds. And I write that because we're going to talk about least upper bounds also. I know, someone made a face when I said least upper bound. I bet you hated those in math. Okay, so upper bounds are all the things I can reach from 1. So the least upper bound is the minimum. If you draw the Hasse diagram that just has the upper bounds and you leave everything else out, if there is a minimum, that is the least upper bound. So the least upper bound, let's write that down. So it's possible actually to have upper bounds but not to have a least upper bound because I have to have a minimum. So if there were several minimal elements out of the upper bounds, then I can't have a least upper bound. So in this case, I'll actually circle the upper bounds and just look at that part of the Hasse diagram. So what is the least upper bound for 1?
1.
1. The least upper bound for anything is always the same point. It's if I have multiple things I want to do the least upper bound of, then I don't have to worry. But the least upper bound here for 1 is just the point 1 because that is the minimum out of all the upper bounds for 1.
So it still counts even though there's not a minimum in the whole diagram?
There's not a minimum in the whole diagram because I'm just looking at the upper bounds.
Oh, okay.
It's the least upper bound. So you're just looking at the Hasse diagram for the upper bounds and finding the minimum of that. That's what the least upper bound is. And so if you remember when you were talking about least upper bounds, like in math a long time ago, you could have drawn a Hasse diagram for things you were looking for that, and it would have corresponded to the same thing. So let's do a little bit with lower bounds also. Actually, let's do a combination of upper bounds. So I want to do the upper bounds. So if I want to do the upper bounds of the set 1 and 4, that's equal to the upper bounds are for 1 intersected with the upper bounds for 4. Okay, so the upper bounds for 4 are 4 and 2, right? And the upper bounds for 1 are 1, 4, and 2. So if the upper bounds for both are 4 and 2. So upper bounds of 1 and 4 is equal to the set 4 and 2. And the least upper bound is what?
4.
That's equal to 4. So I can just write 4 because it's not a set. Least upper bound is always just one thing. Upper bounds is going to be a set. Least upper bound is just one thing because it's the minimum of the upper bounds. There's only one.
But is it still a set with one item in it?
No, it's not a set with one item. Least upper bound is always one thing. So if I wrote a set, I did write a set before. Least upper bound is not a set. Upper bounds always is a set. It's not really that important because I don't mind if you mess up with the set notation on this, just so you know which ones they are. Okay, so technically it is not a set. All right, so we have actually sort of the reverse of this with lower bounds and greatest lower bounds. Okay, so I could do the lower bounds for 2. So the lower bounds for 2 are all the things that I can reach by going down from 2, which includes 2 because 2 has its own arrow also. So the lower bounds for 2 is actually everything because 2 is a maximum. Right, so 2, 4, 1, and 3 are all the lower bounds for 2. What about lower bounds for 1?
1.
Lower bounds for 1 is just 1. And lower bounds for 3 is just 3, right?
Yep.
So the lower bounds for the set containing 1 and 3 is the intersection of these two, which is
Empty set.
the empty set. So there are no lower bounds for 1 and 3. If there was a minimum, there would be. Okay, so how about the lower bounds for 4?
4, 1, and 3.
That's 4 and 1 and 3, right? So let's do the lower bounds for 2 and 4. That's the intersection of the lower bounds for 2 and the lower bounds for 4. So that gives me what?
4, 1, 3.
4, 1, 3. And so what is the greatest lower bound for that?
4.
4.
The greatest is the maximum out of all of those. So I circle that part of the Hasse diagram, and the maximum there is the greatest lower bound. So that's 4. So if you keep your head on straight and you see GLB, just remember greatest lower bound, and then forget the G, do lower bounds, and then figure out the maximum. Yes.
Why is the lower bound for 2 and 4 doesn't include 2?
Doesn't include 2 because 2 is not a lower bound for 4. The lower bounds for the set containing 2 and 4 are the lower bounds that are lower bounds for both 2 and 4. But since 2 is not a lower bound for 4, it can't be a lower bound for the set containing 2 and 4.
All right.
That's why it's the intersection, that's why. Okay, so most of these things that we've been doing with binary relations and Hasse diagrams all just have to do with definitions and applying the definitions. So if you remember the definitions, you can keep applying them and just check them. So the tutorial for binary relations is going to be ready by the end of this week, and I will send you an email as soon as it's ready for you to do, and you'll be able to do that up through the rest of the semester. But I will recommend that you do it before the test, because it will really help on the test, doing the binary relations tutorial. So I'll be emailing you with instructions for that by the end of the week. I'm just putting in a couple of more data collection things, that's all. And this tutorial is actually a really good one because it also has lectures that you can listen to attached to each section of the tutorial, and you can listen to them as many times as you want to. And it also has little exercises you can do, like every time it has a definition, you check it. Like it asks you 3 questions and you do them over and over again. It has a little test at the end too. So this one's going to be much less painful than the proofs tutorial, and you won't have to print anything out except the survey. Okay, the next thing I wanted to do, just for the last few minutes here, is just start talking about what our next topic is. Okay, our next topic is counting. So all semester we've been counting lots of things, right? We were counting the size of sets, counting the size of power sets, counting the number of rows we needed in truth tables, all kinds of things. Counting intersections, counting unions. And that's because it's important to be able to count how many things I should have in computer science. So if I want to know how many inputs I should have or how many outputs I should have, I need to be able to count sets and know when they overlap. So I actually don't think I need twice as many things as I do. Right? So there's lots of different kinds of counting that we're going to need to do. So there's 2 main kinds that we're going to be talking about. And one is combinations. And the other one is permutations. Okay, so when you read a recipe and it says combine these ingredients, does it matter what order you put them in? No. In a recipe, if they care what order you put, it says put this in the bowl. Then you put this in the bowl. And then you put this in the bowl and then you mix, right? So if it says combine, they don't care what order you put it in there. So order doesn't matter with combinations. Permutations are sort of the opposite. And permute means to change the order. So order matters for permutations. So that's the main difference between these. And a lot of you who have scientific calculators will see that there's a button for combinations and for permutations. And they're usually written like this. If you have combinations, it's written NCR. And if you have permutations, it's written NPR. Not National Public Radio. That's read as permutations of n things taken R at a time. And you don't have to write that down because I'm going to tell you again. I just wanted to do a little introduction today, because I think we had like overload on binary relations already. So you can derive, we're going to have some formulas for combinations and permutations, but you can derive all the formulas from drawing a picture. And so right now I'm going to show you drawing the picture because we're going to be using it for the next week or so while we're talking about permutations and combinations. So suppose I have a set of n things. So there's n things in there, n dots. And I want to pick out some of them. Okay, I want to figure out how many ways there are to pick them out, in what order. Okay, so say I want to pick 3 of them. So the N people are going to be people in this class, and I'm going to pick 3 people who don't have to do tutorials. And this is not a true story. This is just an example. Okay, the first prize winner, wouldn't have to do any tutorials, and the second one only have to do 2 of them, and the third, 1, and the third one only have to do 2. So these are prize winners. So order is going to matter, right? You really care if you're the first one, the second one, or the third one. How many tutorials do you have to do? Okay, so let's just say we're going to have 3. First place, second place, and third place winners. So in the first case, I have N students, and I'm not going to give the same prize to 2 people. So once I take a student out of the sort of bag, have all your names in a hat or something, I don't put your name back in there. So how many choices do I have for first place? I have all the students, N of them, right? So N students. But once I've got a first place winner, how many choices do I have for second place? N minus 1. And the next one, I have N minus 2 because I take out 2 people before I get to the third one. So the total number of ways is just multiplying these. So the number of ways to choose 3 winners out of N, where the order matters, is N times N minus 1 times N minus 2. And you can always draw this picture. So this is permutations of N things taken 3 at a time, or NP3 is what you'd have to type on your calculator if you want to put that like that. You can also write it like this. So the size of the set you're choosing from is at top, and on the bottom is how many you're going to choose. So the bottom one is the number of blanks you're going to draw, and the top one is the set that you're choosing out of the circle. So suppose I didn't know how many blanks I had to draw. Say that there were K blanks. So PNK, or PN, P to the N sub K. You read that PNK. It reads the same way as the function, is N times N minus 1 times N minus 2 down to what? Times N minus K plus 1. Because this wasn't N minus 3, it was N minus 2, right? So P and K doesn't go down to N minus K, it goes to the one right before that. The number just higher than that. Don't you hate those dot, dot, dots? I know y'all hate those.
We do.
All right, so we're going to get rid of the dots. You're going to hate it even more after I get rid of them. This looks a heck of a lot like a factorial, doesn't it?
Yeah.
But not the whole factorial.
Yeah.
So if I chose N of them, it would be the whole factorial, right?
Yep.
PNN would be PNN, N times N minus 1, times dot, 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 times, the last thing would be N minus N plus 1, which is just 1. So the last number would be 1. So this is equal to N factorial. Right? So P and K is actually sort of not all the terms. So it's N factorial over, notice that we didn't have N minus K in there. We didn't have N minus K or anything less than it. So if we divide by N minus K factorial, if we divide N factorial by that, we get rid of all the terms from N minus K down to 1. So this is a nice way to write our permutations without putting any dots. But you get to replace them with your favorite factorial function. So we're going to derive, next week, we're going to derive combinations from permutations. So permutations are the easiest to derive because you can draw blanks and figure it out. Even if you forget this formula, you can always draw the picture and derive the formula because that's how we did it in the first place. And then you'll be able to derive the combinations formula also. So just before you leave, this was without replacement. So anytime you see those buttons on your calculator or anything, it's without replacement. And what that means is you don't put the name back in the hat. So if you choose something, you can't choose it again. It's just like we normally assume for any prizes, you can't win more than one prize. So we'll talk about the difference between with and without replacement next week, and we'll also be talking about combinations. So have a good weekend, have a good Easter, and all that good stuff. See you next time.
Wednesday during class period here?